Somebody mentioned on Piazza that it was hard to understand the lecture without seeing slides. No information what lecture, no information what part, what slides. So I decided just to walk over a couple of problems from lecture 7 and lecture 8. Capacitors 1, 2, 3. One, two, well, C1, C2, C3, and we know that C1 equals 1 microfarad, C2 equals 2 microfarad, C3 equals 3 microfarad, and the applied voltage is 6 volts. And this is from here to here, 6 volts. Well, of course, every capacitor has a certain charge, Q1, Q2, Q3, and a certain voltage. In general, I'm just gonna use a letter V, V1, V3, V2. But C1 and C3 are in parallel, so V1 equals V3. And well, since capacitors are in parallel, we can replace C1 and C3 as one capacitor, C13, and for connections in parallel, C1 plus C3, that's going to be 4 microfarads. Now, not aligned. Now we can redraw the circuit. So it's going to be C13 replaces 1 and 3 and C2. And now we can replace these two with one. Let's call it C123. And because in series we can calculate using that rule, and that gives us 1 over 1 over 4 plus 1 over 2, so 4/3 microfarads. Okay, and now we can use just one single capacitor C123 connected to this battery, 6 volts, and calculate this charge Q123 C123 times voltage, so 4/3 times 6, 8, and from micro, -6 coulombs. And now, what do we say? Well, we know that because this capacitor is equivalent to these two, Q13 and Q2 should be equal to each other, but also to this charge, 1, 2, 3. That's why we call it equivalent. And now we can move back to the previous circuit. This is V13, this is V2. So Q13 equals C13 times V13, and that means 8 times 10 to the negative 6 equals 4 microfarad times voltage. So voltage 13 equals 2 volts. But as we know, the voltage across 13 is the same voltage as supposed to be for capacitor 1 and capacitor 3. So this is V13. So it's 2 volts. And this voltage is supposed to be now 6 minus 2, 4 volts. And how can we calculate it? Alternatively, well, Q2 should be equal to C2 times V2, meaning same charge 8 times 10 to the negative 6 will be equal to 2 times 10 to the negative 6 times voltage number 2. That gives 4, 8 over 2, 4 volts. And now we can calculate each charge. For example, Q1, C1, V1, or 1 microfarad times voltage number 1, which was 2 volts. And that's coulombs. And Q3, actually Q3 plus Q1 should be equal to Q13, because these two capacitors combined are equivalent to this one capacitor. So we could just subtract. Done with this problem. Next problem is this one. So here we got same capacitors but connected differently. 1, 2, 3. Now in the lecture I actually made a mistake here. Brain freeze. So I want to replace these two capacitors with one. Series. So C12 should be equal to 1 over 1 C1 plus 1 C2. And that gives what? 1 over 1 over 1 plus 1 over 2 microfarads. So 2 over 3 microfarads. And now, only now, we can replace these two capacitors with this one and connect it to the capacitor number 3, C12, C3, same voltage. So, as I said, C123, the single capacitor that replaces these capacitors, should be equal to C12 plus C3, and that is 2/3 plus 3 microfarads, and that is 3 times 3, 9, 9 plus 11 thirds microfarads. Well, 6 volts capacitance charge equals capacitance 11/3 times -6 times voltage, so 22 times 10 to the -6 coulombs. If we go back to this circuit, same 6 volts. So this is Q12, this is Q3. Q12 is equal to C12 times voltage and 2/3 times 6 times 10 to the -6. So 4 and Q3 is equal to C3 times voltage, C33 times 10 to the -6 times 618 times 10 to the -6 coulombs, and 4 plus 18, which is Q3 plus Q12, of course, equals Q22 times 10 to the -6 coulombs. And well, now these two capacitors have been replaced by this one. So Q1 should be equal to Q2 since they are in series, but also Q1 should be equal to Q2 and Q12 because we replaced these two with that one. So we know these charges 4 times 10 to the -6 coulombs. And now we can calculate, let's say, this voltage V1 should be equal to Q1 over C1. Charge number 1 is equal to charge number 2 is equal to charge 1, 2, 4 times 10 to the -6 coulombs. And capacitance number 1 is 1 microfarad. So that gives 4 volts. And if it's 4 here, that means we should have 6 minus 4, 2 volts there. All right. Done with this. Moving on. Now, a similar situation, right? Again, I just want to repeat quickly. Oops. The resistor number 1, the resistor number 2, and one battery. And on Piazza someone said, well, we've got a double battery. No, just one bigger battery. That's it. Just a battery. EMF, which is equal to voltage between these two points, and the minus potential can be set to 0. And what is happening to potential? Well, we need to remember now that electric potential here will be equal to the voltage or EMF, and the wire does not change it. So here we get the same, we've got the same potential, and because electric current I travels through, potential drops, decreases to a new value, V1 for example. And Ohm's law says potential difference equals resistance times electric current. But this potential everywhere up to here is 0. Has no potential at all. So the same Ohm's law says now V1 minus 0 equals R2 times I. V1. So V1 is equal to R2 times the current, and actually EMF minus R2 times current equals R1 times current, or EMF equals R2 current plus R1 current, or R2 plus R1 times current. And this is why we say we can replace these two resistors with one equivalent resistor. That's it. What about the voltages? Well, of course, the voltage delta V1 is just potential drop, potential difference. That's it, wherever it is. And of course equals this product, Ohm's law. Same here, delta V2. Well, this is what delta V2 is equal to. That's Ohm's law. And if the question would have been calculate electric potential number one, what would you do? Well, you will use, for example, this equation, and that would be EMF minus this product, right? Or you could use this equation. And now, what now? Now the last connection in parallel. Oops, not from start, I need from start. Where is it? Here, that's what I need, right? In parallel, again, notice that even pictures are different, physically identical. Again, the lowest potential is set to 0, so 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. These blue dots or dashes represent electric potential 0 everywhere. But this potential is not 0, it is equal to EMF of this battery. That's potential. Potential difference across the battery is equal to EMF minus 0. Yeah, that's V plus minus V minus. And this electric potential, of course, remains the same all the way along the battery. That is why these two circuits are identical. I've got exactly the same electric potential here, which is EMF, and I've got exactly the same electric potential here and here, which is 0. So potential difference or voltage here equals EMF minus 0. Potential difference of voltage here equals EMF minus 0, or Greek letter epsilon. And this electric current, of course, will be equal to, well, delta V2 over R2, but they all have the same voltage, EMF. And this current, number one, will be equal to potential number one difference over R1, but it's EMF over R1. And these are different currents in general, because right here, when electric current reaches this point, a junction, splitting point, a current splits, divides. And the law of conservation of charge tells us that if we add these two currents together, we should get the original amount. So I1 plus I2 should be equal to I. Or same here, I2, I1, they join and provide the initial current current Y, current I, current that travels eventually through the battery. Well, that's it.